So welcome to the Stewardship Network's monthly webcast. Really pleased to have you with us. Chris Hoving, great, thanks for joining us. Mary, great to have you with us from Monroe County, Kalamazoo, Michigan. I'm Lisa Brush, and I'm really pleased to be here with Jackie, Jessica, Sebastian, and Lavran from the University of Michigan, where they're going to be talking about quantifying carbon storage with remote sensing techniques. I want to welcome you all to the Stewardship Network's monthly webcast. We do these monthly webcasts each and every second Wednesday of the month, way back before all of us used to not do this all of the time. And so you would find us here on the second Wednesday during the Eastern time zone's noon hour, Pacific time's 9 a.m. hour. So go ahead and put that as a recurring event in your calendar. And if you can join us on the second Wednesday, you will find us here. We have been here for more than 15 years on the second Wednesday, and it's been my pleasure to be with all of you from around the country, as well as with our special guests each month. So as I said, I'm here with Jackie, Jessica, Lavran, and Sebastian. Really looking forward to hearing about your work. For those of you who don't know the Stewardship Network, we are a 501c3 nonprofit, and our mission is to protect, equip, and mobilize people and organizations to care for land and water. So we just have the great privilege to work with people like all of you who are doing this amazing work in the field. We've been doing this for the last 20 or so years. We're a national and international award-winning organization for revolutionizing the way that people care for land and water. We are all about partnerships. You all online are a great representation of the partnerships that we all volunteer to international NGOs, to municipal, state, federal, tribal governments, consultants and students and private property owners and volunteers, people like Chris who work for the state of Michigan. John, welcome from Harbor Springs. I wonder if you all are seeing any spring up there yet. We're starting to see a little bit more down here in Southeast Michigan. And our member communities, our collaborative conservation communities, are really why we are a national and international award-winning organization, because they are geographically place-based local networks that are made up of all of the organizations and individuals who care for land and water in a community. And so it's a super cool chance for everybody who's caring for land and water to come together and learn about what everybody's doing across boundaries, to come up with collaborative projects, to really increase their collective capacity to do the work of caring for land and water in their communities. Because oftentimes, without that network, we tend to work in isolation. We don't really know sometimes what our colleagues and our peers are doing in other organizations. And so they essentially engage in on-the-ground conservation action as well as learning and engagement work. And so a really neat chance to say, hey, we actually don't, in this locality, we don't have, so Chris, I'm gonna pick on you, we don't have somebody who's a climate guy. And we want to learn a little bit more. And so how can we put on events that can bring in somebody like Chris to help us learn a little bit more? I want to thank you all online who are contributors to the Stewardship Network. We are a 501c3 nonprofit, and your support enables us to continue to broadcast these free online monthly webcasts, as I said, as we've been doing for more than 15 years, as well as a host of other programming. So thank you so much for those of you who have donated online. As I said, I'm Lisa Brush with the Stewardship Network, and I'm really pleased to be here with Jackie, Jessica, Lavran, and Sebastian, who are going to share their work around remote sensing. And with that, why don't you all take over the screen sharing from me? I want to encourage you all to continue to introduce yourself in the chat box, use the Q&A box also, and we'll get your questions answered. It's one of the great things about this, where you can type in your comments and questions that you have as we go along. We'll make sure to capture them and get them answered by Jessica, Sebastian, Lavran, and Jackie. So great, I'm going to stop sharing. Vic, good to see you. Glad you're here. Thanks for joining us. And why don't you all go ahead and start sharing?
Cool. Looking good, everyone?
Yep.
Cool. Well, thank you for the introduction, Lisa. We're going to jump right into our project here, which is, again, titled Quantifying Carbon Storage with Remote Sensing Techniques. And I'm Sebastian. Cool. So as just a brief overview of C's Master's projects, and basically how it was is as an organization or business submits a proposal for a project, and the project is based around an issue that is, important to the client, but also has broader implications in the environmental space. And the groups of students working on these master's projects are usually interdisciplinary. We each have our own strengths, and we work with a faculty advisor and a client one-on-one to pretty much produce deliverables that will help address the issue at hand. So for a bit more context on our project, we're working with the City of Ann Arbor, Greenbelt Advisory Commission, and Office of Sustainability and Innovations, as well as a client of or a representative of the Conservation Fund that runs the Greenbelt Program. And for a bit of background on the Greenbelt Program itself, it's basically founded by the Open Space and Parkland Preservation Millage, which was passed by a majority of Ann Arbor voters in 2003, and it extends out to 2033. And basically what the program does is it funds parkland acquisitions within the city and basically purchases development rights so that properties maintain some sort of ecological integrity or agricultural land. And to date, this program has protected over 6,000 acres across 60 plus parcels. So the goals of our project are to basically provide the Greenbelt Program with the ability to assess and report on not only climate regulation, but water ecosystem services for the properties that they have protected. And this is good to report on the properties that are already protected, but also is used as leverage for future acquisitions. And for this presentation, we're going to be focusing on the climate regulation services, particularly carbon storage. And the deliverables relating to this project are a geoprocessing tool that will help calculate these things, these metrics using remote sensing data, and as well as a land cover and land use spreadsheet that sort of gives these ecosystem service values on a per acre basis. The larger implications for our project are that basically shows that there is methodology out there for measuring ecosystem services and reporting on them with minimal field work involved and focusing on remote sensing data that's already out there. And the Greenbelt Program is used as sort of the case study for this in our report. And it also shows that, or it emphasizes the importance of, assessing these ecosystem services so that cities can meet their climate regulation goals. But, first and foremost, being aware of what kind of ecosystem service values are out there and what they're doing, what they're protecting with programs like the Greenbelt Program. And also it just provides further justification for, these environmental efforts. And so as a general overview of the Greenbelt, a lot of it is composed of agricultural land, but there's also a lot of woodlands and wetlands in there as well. You can see where the district extends beyond the city of Ann Arbor and takes up a decent chunk of Washtenaw County.
So as Sebastian mentioned, being able to measure and report on the amount of carbon that's being kept out of the atmosphere is an important step for meeting many of the climate mitigation goals that have been put forth by governments and businesses and organizations. So typically this measurement is done using the rate at which atmospheric carbon is captured and stored, which is known as sequestration, or as the amount of carbon that's being stored in the biomass of trees and woody debris, and also in soil organic matter, which is known as storage. Sometimes both measures are used, but for this project, we only focused on carbon storage because it's a more stable measure and therefore it's more feasible to measure and calculate. So it's also important to know where carbon is being stored in an ecosystem. So in the image on the right, you can see that carbon is stored in the leaves, trunk, branches, and roots of trees, in woody debris, and also in soil organic matter. So we really only focused on 3 main areas for our carbon measures. So for the above ground biomass measures, we just looked at the carbon stored in leaves, trunks, and branches. And then for below ground measures, we looked at the carbon stored in the organic matter of soil. Together, these 3 areas account for about 85% of the carbon that's stored in a Great Lakes forest ecosystem. So while we didn't necessarily measure every aspect of where carbon is stored in an ecosystem, we did measure, or what we did measure covers a large majority of where that carbon is being stored in this ecosystem. So as we just saw, about half of the carbon that's being stored in the Great Lakes forest ecosystem is in the organic matter of soil. So the first goal of our project was to quantify this soil carbon storage. And then to begin this process, we had to understand some of the fundamental properties of soils. So all soils are comprised of three main components: sand, silt, and clay. Different percentages and compositions of these main components kind of help define each of the 12 main soil types, which you can see in the triangle in the middle of the slide there. So for example, loams, which is in the brown in the middle of the triangle, are made up of mostly silt and sand with a lesser amount of clay. Loams make up a large amount of the soils found in the Greenbelt district, which you can see kind of in that darker green on the map on the right. So the varying compositions of each of these soil types leads to differences in a variety of soil variables, some of which will be discussed in a bit more detail next. But crucially, these differences in composition make it so that each soil type is able to store different amounts of carbon. So knowing the values or range of values for certain soil characteristics is key to being able to calculate how much carbon can be stored in a particular soil type. So in order to find these values, we use the Natural Resources Conservation Service, or NRCS's Web Soil Survey. And this tool is pretty straightforward and easy to use. All you need is to input a shapefile of your area of interest, and it generates a report giving values for a variety of soil metrics. So you can see the percentages of sand, silt, and clay in the report kind of on the bottom right there, and saturated hydraulic conductivity, a bunch of different variables. And it'll give it for all of the different soils that are found within your area of interest. So for our purposes, depth, moist bulk density, and organic matter were the most important metrics that we needed. And so then you can also notice that for bulk density and organic matter, there are three values listed for each depth. And so that one's a low, one's a medium, and one's a high value. So that'll come into play next. So then we took the values from the Web Soil Survey report and we put them into an Excel table similar to the one that you can see here. We took the depth, density, and organic content values for each of the different named soils that we had within the Greenbelt district. And then we plugged those into the equation that you see above, where the depth of the A horizon, bulk density, organic matter content, and a constant of 0.47 are multiplied, and you get kilograms of carbon storage per unit area. So for this, as I mentioned before, there's a low, medium, and a high values for bulk density and organic content. And so we chose to use the medium values for our calculations, just to give us a more conservative estimate for the soil carbon. So then we use these medium carbon numbers, which were highlighted in blue there, as the inputs to our model in GIS.
Hey, Jessica, let me ask,
Yes.
B asks, does the acidity of the soil increase with carbon storage and affect the organisms that rely on it? She says, I think that's what happens in aquatic ecosystems. Do you know that?
We don't know the answer to that, but that equation should account for the average soil carbon stored without acidity being a factor.
Yep. Mm-hmm. Cool. And then if anybody else online who's there knows the answer to that question that's in the Q&A, go ahead and give us an answer there. Thanks.
Okay, so I'll move on to our models that we developed in ArcGIS Pro Model Builder. So Jessica talked about that soil carbon spreadsheet, which you can see in the blue box here, served as input to our first model. And that took carbon per unit area. And our goal was to calculate carbon stored on a property by property basis. So the purpose of these models was to make it adaptable so that all you had to do was input the shapefile of a property boundary, and you would get the amount of carbon stored in forest and wetland soils. So this will produce a shapefile of carbon in kilograms per meter squared for a single property. So next, we just made a table for all of the properties in the Greenbelt, looking at their forest and wetland soils. For example, that first property had approximately 11 million kilograms of forest soil carbon and 98 million kilograms in wetland soils. This particular property was really high because it was mostly wetland and it contained a lot of muck soil type, which is really high in organic matter content. So that's why it's so high compared to the other two, even though it's not necessarily very large in size. And then later on at the end of our presentation, we'll show you how we converted these values into the social cost of carbon and other ways of looking at ecosystem for service values. Okay, and then transitioning, or also I wanted to point out that we only looked at forest and wetland soils. We could have also applied this methods to agricultural soils, which is the majority of the Greenbelt. However, there are so many factors that can affect how much carbon is stored in agricultural soils. For example, different agricultural practices that may lower the amount of carbon. So we only applied this to forests and wetlands because we were more confident in those land cover types. Okay, so now transitioning to above ground carbon storage, which is just the carbon stored in trees. Above ground carbon storage can be estimated with biomass estimates, and you can do this knowing tree species DBH and allometric equations. However, if you want to do it on a much larger scale, it's very difficult to use just field work alone. And so that's why we wanted to incorporate remote sensing techniques. And in order to use remote sensing and develop models, you need to have some field measurement to use as training data. So that's the first part shown in green there. That's what we're going to go over first.
So when you're collecting this field data, there's a few steps you have to follow. So we're going to go through the methodology here. So the site locations we chose to study are Brower Preserve and Sire Woods out in the west, and Creek's Head Preserve in the northeast of Ann Arbor. And these properties had a different mix of forested areas, so they were a good representative sample, we thought, of the types of forested areas you'd find in Greenbelt properties, as well as Sire Woods being one of them. So the first step is preparing a map when you're going out to the field, so you know which plots you're going to. So this is done in GIS. We created a shapefile of the property and then created we had a randomizing function that put 20 random plots on the map. And the reason we did totally random plots is so that we don't have any bias in our data. And that's really important to do because we don't want to go out to the field and just decide on plots when we're out there, when we see certain trees, or we don't want to pick the areas with lots of trees and ignore the ones with few trees, because then we're just ending up with overestimates or potentially underestimates as well. So randomizing function was used to eliminate that kind of bias. And so when we created this map, we then exported it to an app called Avenza, which you can use on your phone. And this is the Sire Woods on the right. And so this is Avenza in action in Brower Preserve. And so you can see you can follow where you are on the map, and you can see which points you've been to already, and you can mark them so that you're making sure to hit every plot. Because of the randomizing function or using it, it's a bit difficult to we have no control about where the points end up. So some of the points inevitably end up on the border of the property or very close together. So there's a little bit of work to be done in sort of deciding which points were actually usable at the end of the day. But for the most part, it was very, very simple to get the work done this way. So when we got to the plot, the first thing we did was mark it with a GPS point. We used a Trimble R1 device. It's basically a GPS unit that would work a bit better to your phone. We connected it using Bluetooth. And so we would look for, we would wait for the signal to establish until we had, about a 1 meter or less uncertainty in our placement And then we would basically mark this plot in the ArcGIS Online collector app, and basically make this point upload into the cloud so that it's stored for future use, and that we could download it at a later date. Then we marked all the corners of the plot because we were doing 10 by 10 meter plots, just squares. And so we need to determine which trees fall within the plots.
Okay, so the next step was measuring trees within all the plots. And in order to find the carbon stored in a tree, you first need to know its species and diameter to calculate biomass using an allometric equation. So here on the right is an example of what a plot would look like. It's just a 10 by 10 meter square plot, and each of the green circles represents a tree. So we measured all trees that were at least 10 centimeters in DBH, or diameter at rest height. And we also took note of the tree species and its relative crown position.
Not sure what happened there. Sorry, jumped all the way to the end.
Spoilers.
To wrap up.
There had to be some issue in there somewhere.
Exactly.
Okay, so across our 3 study sites, we found at least 25 different species. The most common ones at Sile Woods and Creeks Head Preserve were sugar maple and Tilia americana, or American basswood, and at Brower Preserve it was mostly red maples and silver maples. So all of these species belong to a species group, as noted in the table on the far right column. The study done by Jenkins et al. In 2003 looked at every species in the United States and sorted them into 10 different groups based on how much biomass is stored in that particular species group. So the 3 species here on this slide, Tilia americana belongs in the mixed hardwood group, Quercus alba in the hard maple, oak, hickory, beech group, and Populus deltoides in the aspen, alder, cottonwood group. So it was essential to know the tree species. You didn't even have to identify it to the species level, but to know which group it belonged to so that you could calculate its biomass. So here's a table from that Jenkins paper showing you all the different parameters. So that equation in red is what you use to calculate biomass in kilograms. And all you need are its DBH in centimeters and which species group it belongs to. So you know which parameters to use in the equation. So we did that for every tree. In order to get to plot level biomass, we first had to calculate biomass for each individual tree. So for this first tree in Sile Woods, it was an Acer saccharum. It was in that hard maple oak species group. And with a diameter of 14 centimeters, that came out to 82 kilograms of biomass. And approximately half of that biomass is carbon. So this one tree had 41 kilograms stored in the above ground component. So we could continue this sampling method for all of the Greenbelt properties. However, it's very time intensive to do that, and a much easier way to look at biomass is to actually use remote sensing data.
So yeah, as Jackie said, after we finished our field measurements, our second step was to measure the tree heights using lidar data. And so the second data type in our figure here was came from airborne lidar. And we use this in conjunction with our own field measurements because it allows us to be able to infer relationships across a much wider area. So we didn't have to do as much of the field sampling. So then by using remote sensing, we were able to take the field measurements that we did do in a few representative locations and then scale them up to the Greenbelt district or even Washtenaw County as a whole. So for our project, we did this using light detection and ranging, which is also known as LiDAR. It's an airborne remote sensing technique. And for LiDAR, short pulses of laser light are emitted from a sensor, which is attached to an aircraft. And then when the pulses reach an object, whether that be a tree, a building, or something else, they will reflect off and then return to the sensor. And then the time interval from when the laser pulse leaves the sensor to when it returns is then used to calculate the height of the objects below that were hit with the laser pulses. So this image is just an example of a point cloud output from lidar returns. And as you can see, the different colors represent different elevation ranges in feet above sea level. So this can give us a fairly accurate idea of the tree heights in a forest just from using lidar data.
So from these point clouds, we can create what are known as canopy height models. And a canopy height model is essentially just an image where each pixel value has a height value associated with it. And this height value is just the height at which the laser bounced off something and returned back to the sensor. Go to the next slide. So how can we use these special pictures that were created with lasers to figure out how much trees weigh? Well, we can do this by extracting the pixel values that fall within each plot that we sampled and analyzing the distribution of pixels, and then comparing it to our in-field biomass estimations. So in order to infer this relationship, we need to choose an appropriate statistical model, though. So several studies, such as Gleason et al., have used forest height percentiles and crown geometric volume percentiles to infer biomass. So from the distribution of pixels for each plot, we were able to infer the relationship between height and forest biomass by calculating predictor variables. And these predictor variables were just used to say, for a 1 unit increase in the predictor variable, what is the increase in biomass for a given plot? So of the predictor variables that we used is we used the maximum height, so the highest pixel value that fell within the plot, the minimum height, and then various height percentiles increasing in increments of 10. We also looked at the crown geometric volume, which is just the volume of the canopy at different height percentiles. So for example, the crown geometric volume at the 50th height percentile is the volume of the canopy that falls below the 50th height percentile that we just calculated. So in order to find out which predictor variables were important for our model, well, we used AIC, which is for those of you that aren't familiar, is a metric for assessing the goodness of fit for a model. And you're penalized for including redundant predictor variables. So a better AIC score is a lower one. So for each model type created, the combination of predictor variables that yielded the lowest AIC value was nominated as a candidate model to be compared to each of the other model types. Well, what do I mean by different model types? There are several different model types that have been used in the literature to infer the relationship between height and biomass. And some of the model types that we tested was ordinary least square regression, power law models, fixed effects models, random forest models, and support vector regression models. We then compared the effectiveness of these models on holdout training data set. It's to help further remove bias from our study. So some of the preliminary analysis that we observed is that the fixed effects model had the highest, explained the largest amount of variation within the data set, explained the largest amount of variation on a holdout testing data set, was the most statistically significant model overall, and had the lowest root mean square error kilograms of biomass for a given plot. These numbers, which is important to note, are a little variable, though. We haven't done any cross-validation, but which we're going to eventually in our final report. But the general pattern seems to be evident in any of the random samples that we produce. So in summary, the fixed effects model explained the largest amount of variation in the training data. This is probably likely due to some of the clusteredness of our training data. Whereas the machine learning techniques such as random forest and support vector regression performed poorly. And this is most likely due to the small sample size that we had as well as the lack of diversity. So for example, how machine learning works is more information you give a machine learning model, the more accurate results you should expect. So for example, if you wanted me to identify fruit and you only showed me different types of apples. As soon as you show me an orange, I'm going to likely think that orange is an apple because I've only seen apples before. However, if you show me grapes, if you show me pears, there's all different types of fruit, I'm much more likely to identify fruit correctly because I've been exposed to all these different types of fruit. So using these models, now that we've created these models, we can create a biomass raster. And just like the canopy height model, this is just an image where, except now, every cell represents the estimated biomass for a given 100-meter squared area. This is useful to practitioners because using GIS, you can just add up all the pixel values in an area of interest and figure out how much biomass is in that area, and then in turn, how much carbon is being stored in that area and not being released into our atmosphere.
So overall, for this project, we were able to accomplish really three main things. First, we were able to estimate below ground soil carbon storage by building a model in GIS using data from the Web Soil Survey. And then second, we were able to estimate above ground carbon storage in biomass by applying modeling techniques to lidar data. And then third, we were able to communicate these values in terms corresponding to equivalent measures. So for example, on one 91-acre property that we looked at, which has 5.3 million kilograms of soil carbon stored, we can say that it contains the carbon equivalent of the annual emissions of 443 average Ann Arbor households, or the equivalent of over 220,000 airline miles, which is about 11 round trips between New York and Sydney, Australia, and over 13 million passenger vehicle miles, which is the equivalent to the average yearly mileage for like over 975 drivers in the United States. So being able to communicate these values in terms that people can understand better is helpful for reporting and assessing their value. So some limitations and recommendations. First, our models, or our first limitation was really that our models are specific to Washtenaw County and Southeast Michigan in general, but anyone can follow our same methodology and it will become useful in other areas and regions. And then a recommendation is collecting a larger abundance of and more diverse field data will lead to more robust estimates from the machine learning algorithms used in the modeling. And then third, we did only look at forest and wetland soils and not agricultural soils, which, as was mentioned in the very beginning, cover a large portion of the Greenbelt. So we are definitely underestimating the amount of carbon that's stored in soils in the Greenbelt, but agricultural soils tended to be very difficult to measure because of variations in practices and crop types and things like that. So we did not look at those. So another limitation of our project. So thank you all for listening. We would like to thank the City of Ann Arbor Office of Sustainability and Innovations for helping fund this project, and then our advisors, Dr. Schuler and Shannon Brines, our client, Remy Long, and as well as a handful of our collaborators, including Jason Talent, Manish Verma, Bennett Fober, Kevin Harnish, and Colin Carroll, and the folks at Neon for their help and support throughout this project. And then, yeah, we've included our individual emails as well as our group email. So feel free to contact us with any questions.
Great, you all, thanks. This is really, really neat project, right? And one question for you all, when you started out, had you all done any study like this before?
No, I think this is brand new for all of us.
Exactly, great, nice job. And I also want to say, really nice explanation of it, right? Like even in the beginning, we had talked about how, you know, some of what you're doing is super duper technical. And so kind of did a great job of presenting that information. Can you share a little bit more? Do you know, and maybe some of your collaborators who are online here with you, this is a question about kind of how will it continue to be used? And then one of the questions about, so this is, Pete, this is a good question. So are your biomass, oh, Pete went away for a second. Are your biomass estimates, let me bring you back here. I think the question was about, are they for one point in time, right? So how do you, how do you do this carbon measurement over the course of time? Is it one course of time? And then certainly if it's disturbed, then it changes everything. But any thoughts about that?
Yeah, it's just, unfortunately, it's just a snapshot in time. If you wanted to understand how it would change in time, you'd have to look into carbon sequestration, which unfortunately we didn't have the time to do. But that would be the way you would go about it. But that is it's very difficult and time expensive, unfortunately, in 2021. But that's the way that you would project it through
Yep,
time.
that's great. And then folks who are online also who've done a lot of this work, feel free to chime in with some of your thoughts about how kind of how we do that over time. So Brandon also asks, what are your thoughts as to how the above ground model with the lidar done on a tree species group, or were all tree groups grouped together? If done all together, do you have a feeling for how the results would change or improve with a tree classification using imagery prior to model selection?
Yeah, I don't know if anybody else wants to jump in. I don't want to be sucking up too much of the oxygen, but so we did. It wasn't there wasn't any trees were treated the same no matter what species they are, and that was definitely a source of error in our model. A lot of other papers use mixed effects models, so we used a fixed effects model. But a mixed effects model is when you incorporate random effects, and what a lot of other papers do is they use tree species as actually a random effect in their model. And this has been shown to greatly increase the accuracy of the model. That's one of the things also we just didn't have time to do and our study system didn't allow, but that is something that's highly used in the literature and has yielded very good results.
Very cool. And then Bill also says you can also go, so kind of now that you've got the model trained, you could also rerun the model with an updated LiDAR data set with new tree heights. And then you would assume that the field data you used to train the model would still be valid. So kind of that the Greenbelt group will be able to kind of continue to use your model over time.
I also like to add that even though it is a snapshot in time, like we're using 2017 LiDAR data and then our field measurements were done in 2020. The whole purpose of the Greenbelt is that it's all conservation easements. So the forested land cover types of the Greenbelt are not going to be changed. So that's why we were able to make these carbon storage measurements.
Yeah, that's great. And that's the excellent point for why having programs like Greenbelt and land conservancies and land trusts and parks and all of those things are so valuable. Can you all speak to, Stephanie asks, how does the quantity of carbon storage change seasonally?
Well, I think as we saw in the diagram towards the beginning, I think it's only roughly 1% of the biomass is actually stored in the leaves. So for the obviously the tree growth depends on the season as well, but we're taking a snapshot of basically what is stored in the wood. So from that regard, the biomass does is decreased in the winter months when the leaves aren't there, but for the most part, the biomass should be pretty constant. And obviously the tree growth is occurring over time in the properties that are conserved and where trees aren't being cut down. So an updated LiDAR data set would give you an idea of how the biomass is changing over time as well. What kind of rates you can expect of increase. But obviously that takes multiple different data sets and probably new field work involved as well. But yeah.
Yeah.
And if you
great.
did want to look at those seasonal differences, that would be, you would need to measure carbon sequestration for that.
Mhm.
So.
And then Stephanie asks, is the carbon storage in a tree always half the biomass, or does it change based on species? I kind of had the same question when you all were talking about that. Yeah, how does that work?
Yeah, that's been shown by several studies that would actually cut down trees and weigh the oven dry biomass to figure out how much carbon is stored, and it's been known to be about 50%, and that doesn't vary by species.
Interesting. That's very cool. And one of Gary asks, and then Chris kind of answered, would some of the carbon stored in soil, is it a different chemical form than that in water? Do you all know the answer to that? Okay. All right.
Know
Exactly.
anything about chemistry, so
Right. More good questions.
I was lucky to survive in the undergrad, so.
Exactly, right? And then Chris points out that you can have high carbon in both high acid and in low acid. So in a bog, a high acid in a bog, and low acid in a fen. And I'm not sure what effect increasing carbon would have if all else was kept the same, but it probably depends on the chemistry of the carbon. Jessica, in the very beginning, you were talking about a formula. And where did that formula come from? Is that from the lit?
It's not from the literature. We had discussions with a professor at SEAS, Dr. Don Zach, and he gave us that equation. So that's where that came from.
Okay, so that's Don Zach equation. We can go back and talk about
yes.
that. Yeah.
Yes.
And then also want to just point out that there's people are singing your praises. Great presentation. I'm a SNRE alum interested in applying your model to the Forest Preserve District in Illinois that I work for. Can you share it with me? So let's maybe one of you can type in the chat. You guys are greenbelt21 at umich.edu.
Yeah, I'm typing in our email address to the chat there.
Yeah, we would absolutely love to. So yeah, we're really excited that you're interested in it.
Yeah, it's a super cool model. And then a question that Bing asked that maybe is to you all, but maybe also to the attendees: how accurate is the USDA underground biomass estimation? Any sense? I mean, we take it on faith, but maybe some of the folks online can let us know. But
you mean the web soil survey, or?
yes, yeah, yep.
I think that's something we just sort of take for granted, is that they're going to have the best source of data out there. So yeah, I don't know. I can't remember what the cell size resolution is that on, Jackie, if you can remember that.
Yeah, I don't remember what the resolution is. It's more about, it's not really spatial. It just tells you what soil types are found within your area of interest. And then based on the soil name and all of the metrics it provides, like horizon depth and bulk density, you can calculate the soil carbon storage there. Okay,
great. And then here's a question about kind of from the managed ecosystem kind of piece. So Katie asks, she's interested in using cost-effective carbon modeling for monitoring effects of forest management practices as part of ecosystem service monitoring. Is there any refinement of this process that could be used cost-effectively for forest monitoring on managed sites? So any sense of that? It seems like it wouldn't necessarily be that different, but.
Yeah, there are a ton of different applications of lidar for understanding forest structure, and so we used a lidar data that was given to us by Jason Talent and Shannon Bryans. But if you're interested in getting your own lidar data for a specific geographic region, there's a nice R package called JEDI, and that's an airborne sensor. We used a lidar that's collected in a plane. This was collected from a satellite, but yeah, that's definitely something to explore if you're interested in obtaining your own LiDAR data. But then there's several different vendors, and
Cool.
there's a lot of options out there.
Yep. And then was the LiDAR data done during leaf on? Do you know if it was when the trees were in leaf?
I
Question
think it
from
was over
Charlie.
the summer. I don't know. I'd have to check.
So.
Okay,
But I
great.
think
So
it was
Jessica thinks so.
Leaf off.
Oh, leaf
Jason
off.
Talent
Oh,
says
wait,
leaf off.
leaf off. Okay.
Leaf off.
Jason,
Okay, great.
Yeah.
There we go. Thanks. I figured one of them. So then also really interesting question. So from Chris, so it's about carbon soil storage. And so any sense of how carbon is stored differently in prairies versus forests? So is there more soil? Is there more carbon in the soil if there are fewer trees? Do you know anything about that?
I would assume that's true because, or even in a forested ecosystem, as that diagram or that picture that Jessica was talking about, it showed the different percentages of how much carbon is stored in each component. Even in a forested ecosystem, 45% of that was in soil. So I would imagine if there are fewer trees, that would only increase, like not necessarily more carbon in the soil, but relatively compared to how much is in the shrubs, a higher percentage.
Great. And then one of the questions, so Phil asks, and you all might not be able to do this, but maybe JT or Shannon or others online, can you all come, because you all got the LiDAR data, but can someone comment on the complexity and cost of conducting a LiDAR survey? Hey, and then shout out for next month, where we're going to be talking about remote sensing again. So second Wednesday we're in March already, aren't we? Second Wednesday in April, tune in again, and we'll be speaking with somebody who's been doing this remote sensing work for decades. So,
Well, for the cost of conducting the survey, we were lucky enough to get access to the data from SAMCOG, which is for the entirety of Washtenaw County. So if there is some inroad you have there, to get access to this data for free, and there's a lot of different connections out there, then by all means, explore those. You can conduct your own surveys with things like drones, but in general, LiDAR sensing is fairly expensive.
right.
So definitely worth trying to see if anybody you know has access to it and is willing to share.
A question for you all. One of the questions that I was wondering is how kind of expensive and complicated would you say this survey would be to do? As Peter, I think it was Peter who said he wants to use this same model. Like how, if somebody wanted to start to do this in their area, and you've certainly outlined the methodology for people to follow to do, but any sense of how complex and
Well,
go ahead, Evan.
No, I was just gonna say the big upfront cost is actually obtaining the LiDAR data. Is we pretty much didn't spend any money at all, and we just did this all on our own personal computers. So that's just a big upfront cost. So if you can get LiDAR data from a friend, or like as I mentioned, Jedi is also a very a good resource. Other than that, it's a little complicated, as I think you noticed from our presentation, but it's not as bad as you think. So it's definitely doable, especially if you have remote sensing experience. It's very doable. I don't know if you guys like to add anything.
Depending on the size or how accurate you want the results to be, it is possible to just do a lot of field work. Like if you're just looking at tree biomass, just using those equations from the Jenkins paper, you can figure out how much biomass is stored in those trees, just knowing the species and diameter.
Yep.
But if you are looking to scale it up to a really large site, that's when you'll want to look at LiDAR data.
That's great. And I will, so next month's webcast is seeing the trees from the forest, individual tree classification from imagery and LiDAR. So again, a chance to do that. So another question for you all about the, so super cool stat that you had about the 91 acre property and the 5.3 million kilograms of carbon stored. How did you do the conversion when you said, which was great, like putting that in terms that we could understand, 443 average households or 13 million automobile miles or something like that. But how did you do that conversion?
There are independent websites and organizations out there that work on making estimates that are as accurate as possible. But the vast majority of our conversions like that, and that'll be in our final report as well, are straight from the EPA. So they're about as high up as you can get for those estimates.
And then we just took the kilograms of the soil carbon and we then converted that into like carbon dioxide equivalents, and then use those with, like Sebastian said, the EPA numbers for average emissions from a household and vehicle miles and airline miles, and then we use those to make the equivalents.
That's great. And I would also encourage people to peruse the chat, because there are a lot of folks who are sharing where LiDAR data is available. So make sure that you, from the USGS and other sources. So, and then this is another good question that I had wondered too. So based on the species and the DBH and the height, is carbon storage fairly constant, or is it, among those, I think you said there were 10 classifications of trees?
Yeah, so the Jenkins study grouped species into 10 different groups. And you actually don't even need height for that. It's just species group and diameter. And that's to calculate the biomass. So for each species group, it's going to have a different amount of biomass depending on different properties of that species. And then for all of the 10 groups, the 50% of biomass as carbon is a constant measure.
Great. And then let's also just point out that there are some folks who are saying, hey, they'd like to have access to this as a paper if you all do that. And Sheila Schuler points out, who is your advisor, that all SEAS master's projects are available at Deep Blue Library in the document, so you can search for those. And then any thoughts about whether or not you all might publish something?
Yeah, I mean, our report for this project will definitely be out at the end of April, and we're hoping to publish our methodology for the above ground portion to a journal, but we haven't decided which one yet.
Yeah, finish up the project first, right?
Yeah, exactly.
Exactly. Get to graduation. What about thoughts? Somebody else asks, do you think this could be applied to a small site, like just a 1 acre site? Could you just do that there?
Yeah, absolutely.
Yeah, that's what it seemed. Yeah. And then are you at the place where you are, where you're kind of coming up with recommendations and conclusions for decision makers with this?
Yeah, I mean, at the end of the day, it's meant to justify further, conservation, which is, obviously the goal. But, some of the smaller recommendations, we can, fairly plainly make that, there seems to be a lot of carbon stored in, for example, wetland areas. So, prioritizing those is definitely a plus. Also, the more heavily forested an area gets, the more carbon you're going to get from the above ground side as well. Yeah, I don't know if anyone else has any thoughts on that.
Yeah, it just seems like it's another ecosystem service. Like, yes, nature is actually really important for us for many different reasons, and this is another one of them.
And in the final report, there will be a section on on water quality as well. We didn't talk about it in this presentation, but yeah, there will be some general recommendations with regard to that as well, especially with preventing land conversion, and which is again further justification for keeping these areas forested or agricultural areas rather than low density residential.
Yeah, interesting. Give us the 30-second water quality piece that will be in it.
Oh, well, basically we looked at for the most part nutrient load reductions and heavy metals in particular. the latter of which seems to be the heavy heavy prioritization, especially when preventing areas from becoming commercial or in industrial. Yeah, so we have estimates we've made, and we have a simplified version of one of the EPA's nutrient load calculators that we're going to hopefully make more publicly available, and as well as we're working with a team at MSU to hopefully get some of their public data a bit more useful for the Huron River area, and yeah, hopefully that's on the horizon.
Great, thanks. So any kind of, as we're coming to the top of the hour, any kind of closing thoughts or remarks that you would want to make?
Well, I think for the most part, we just want to say thank you for everyone for joining and trying to learn about this with us. And it's especially great to see everybody in the chat, throwing out the ability to get lidar data and where you can get it. And we're not all knowing, but yeah, we appreciate everyone trying to make this project as far-reaching as possible. And fingers crossed, this becomes a regular thing that cities start doing, is taking inventory of their below and above ground carbon.
That's great. Well, thank you all so much, Jessica, Sebastian, Lavran, and Jackie, who are students at the School of Environment and Sustainability at the University of Michigan. Really pleased that we were able to have you here. And yes, we always archive these. They're on our website, stewardshipnetwork.org. And on our webcast page, you'll find a link to the archives. And there is, again, I want to encourage you all to attend next month, April 14th, Eastern Time Zone's noon hour. And then also want to just point out that there's a SavannahInstitute.org Agroforestry 2021 that's all about carbon drawdown. So that's a conference that I take it will be online that might be of interest to people. Learn a little bit more about that. That link is in the chat. Thanks for pointing that out. And I want to thank you all for sharing your hour with us. And thank you all to all of you online who are part of the Stewardship Network's monthly webcast. And Sebastian, as you say, one of the great things about this is our audience is an awesome audience with all kinds of experience and great questions, as well as knowledge to contribute to it. So I want to thank you all online. Thank you for presenting. Really a pleasure and really great presentation, really fascinating work, and also helps give us the justification for the work that we do, that we can talk to decision makers about quantifying some of the benefit of what we know inherently.
Thank you for having us.
Yeah,
Thank you for having us.
thanks so much. We'll look forward to staying in touch.